Alright, let's talk about 3.3, derivatives of exponential and inverse trig functions. We're actually, in this section, going to start off by looking at just the derivative of inverse functions in general, okay? And this notation might be a little bit confusing, so just to kind of explain it, first of all, when you see a -1 in the exponent, right, on a function, that doesn't mean f to the -1 power. So it doesn't mean 1 over f. It means f inverse. And f inverse is not necessarily the same as 1 over f, right? But anyway, we're taking f inverse prime of x. That is, we're taking the derivative of f inverse of x. And even though f inverse is not necessarily the same as 1 over f, when you take the derivative, you do get something that looks kind of like that, right? So f inverse prime of x is 1 over f prime of f inverse of x. Okay, provided, of course, that the denominator is not 0. And here's a proof of that fact. So, and this proof is going to be important because it's going to be a technique that we use when we're looking at exponential and inverse trig functions, as well as a couple other things, right? So first of all, we're going to let y equal f inverse of x. And that statement is equivalent to saying, right, if you take f of both sides, then you get f of y equals f of f inverse of x. But the f and f inverse will cancel, so you get f of y equals x. Or in other words, x equals f of y, right? So this statement is equivalent to that one. And now you can differentiate this one with respect to x, right? Derivative of x is 1. Derivative of f of y is going to be chain rule, right? So it's going to be f prime of y times dy dx. And then solving for dy dx, you get, 1 over f prime of y. What was y? Well, y was f inverse of x. So this is really 1 over f prime of f inverse of x, right? And that concludes the proof there. So that's one fact that's important. Now another fact that's important is, well, how do we establish that f inverse exists in the first place? Because you may know from your previous algebra experience that not all functions are invertible, right? Not all functions have an inverse. So how do we know if a function is invertible? Well, we know it's invertible if it's 1-to-1. But what's another way to know that a function is 1-to-1? Well, it turns out that all monotonic functions are 1-to-1. Okay, what do we mean by this word monotonic? A function is monotonic if it's strictly increasing or strictly decreasing. Okay, so if you have a function that's strictly increasing or strictly decreasing, then it's 1-to-1 and hence invertible. Let me draw a picture to help you understand what I'm talking about. So here's an example of a function that would not be monotonic. So if you had something like this, right? This is not a monotonic function. It's not strictly increasing or strictly decreasing, right? It increases from here to here, but then it decreases from here to here. So this is not monotonic at all. A monotonic function would be something maybe like this, right? Strictly increasing. Okay, that would be a monotonic function, and it's clearly 1-to-1, right? Because it passes the horizontal line test. Okay. Or it could be, strictly decreasing, and maybe it does something weird, right? Like maybe it does, like, it's got a hole and then a little jump and then continues on down like that. But this would still be a strictly decreasing function, and you can see that it also passes the horizontal line test, so that it's also 1-to-1. So both of these functions would be invertible. This one would not be invertible. Okay. Now, how do you tell if a function is strictly increasing or strictly decreasing? Well, if f is strictly increasing, then its derivative would have to be positive for any value of x, right? That makes sense, right? If it's strictly increasing, then its rate of change is always positive. And then similarly, if it's strictly decreasing, its rate of change is always negative. Okay. So what I want to do is give you an example now that sort of ties these two facts together and sort of lets you know why they might be sort of interest to us. So let's let f be x to the 5th plus x plus 1. And first of all, let's show that f is 1-to-1. Okay, so there are a couple ways you could approach this, right? So one way that you can show that f is 1-to-1 is to appeal to the definition of what it means for a function to be 1-to-1. Okay, a function is 1-to-1 if f of b equals f of a implies that b equals a, right? That's not the approach that we're going to take here, though, right? That's one way that you could go about trying to show it. But another way that you could show it is by appealing to the fact that we just talked about a second ago, right? If we can show that f is monotonic, then f would have to be 1-to-1. And how can we show that f is monotonic? Well, we can look at its derivative, and if its derivative is either always positive or always negative, then f must be either strictly increasing or strictly decreasing, respectively. So let's look at the derivative, right? F prime of x is going to be 5x to the 4th plus 1, right? Okay. Now, this function is always positive, right? Because when you plug in a positive number and raise it to the 4th power, well, it's still positive. And then when you multiply that by 5 and add 1, well, it's still positive, okay? But if you plug in a negative number and you raise it to the 4th power, then it becomes positive, right? So whether you plug in a negative or a positive number, this thing is always positive. And if you plug in 0, by the way, you just get 1, which is still positive, right? So this function is always positive. And therefore, so the derivative is always positive, and therefore f is strictly increasing. And therefore, f is 1-to-1. And we could take it one step further and say, therefore, f has an inverse, right? And so since f has an inverse, maybe we're interested in knowing what it is, right? So let's find f inverse prime of x. Okay. So again, a couple ways that you could go about trying to do this. Excuse me. One way that you could go about trying to do this is to try to explicitly write f inverse in terms of x. And if you think back to your algebra days, the way that we would do this is we would say y equals x to the 5th plus x plus 1, and then we would switch the places of x and y, so we would say x equals y to the 5th plus y plus 1, and then we would try to solve for y. Unfortunately, that's going to be impossible in this case, right? Y to the 5th plus y plus 1, solving that for y is impossible. Or I don't know. I guess I don't know that for sure. Maybe it's not impossible, but it's very difficult, to say the least, right? So we're not going to be able to do it that way, okay? So we're not going to be able to explicitly write f inverse in terms of x, but we can express it in terms of y, right? We can say let f inverse of x equal y, and then that implies that f of y equals x, right? Or in other words, f of y would be y to the 5th plus y plus 1 equals x. And now we can differentiate this thing implicitly with respect to x, of course, right? So now we're going to take the derivative with respect to x. Okay, derivative with respect to x of y to the 5th is going to be 5y to the 4th times dy dx plus 1 times dy dx plus 0. And this last term doesn't have a y on it, so you don't have to say times dy dx or anything like that. And then on the right hand side, derivative of x is just 1. Okay, so I'm going to factor out the dy dx now, right? We get dy dy dx times 5y to the fourth plus 1 equals 1. And therefore, dy dx equals 1 over 5y to the fourth plus 1. Okay. So there's f inverse prime of x, right? And we got it by doing some implicit differentiation. So now part C, let's compute f inverse prime of 1. This is trickier than you might think, because the implication here is that x equals 1, right? The implication is that x equals 1. But the formula that we got for the derivative is given in terms of y, right? So we're not necessarily going to be plugging in 1 to this formula. We have to figure out what y value corresponds to an x value of 1, right? And to do that, we look at the original function, okay? And we're going to plug in 1 for x to see what we would get for the output, right? So let's see. So f of 1 equals 1 to the fifth plus 1 plus 1. Well, that's just 3. Okay, so y equals 3 when x equals 1. Okay? So f inverse prime of 1 is really means that we're going to be plugging in 3 for y. In other words, I think maybe a better notation is to say it like this, right? So we say dy dx evaluated at x equals 1 equals dy dx evaluated at y equals 3. Okay? That's really the key. And then that's going to be 1 over 5 times 3 to the fourth plus 1. Whatever that ends up being. Did I make a mistake? That seems odd to me. What did I do wrong here? To the fifth plus 1 plus is 3. Yeah, okay, so this is wrong. This part's wrong. So I was plugging in x equals 1 to the original function. I need to be plugging it into the inverse function, and that's why it's tricky. But remember y to the fifth plus y plus 1 equals x. So if I'm plugging in 1 for x, really I need to plug it in. I need to plug it in here. So really I need to say y to the fifth plus y plus 1 equals x, right? Equals 1. That's actually not terrible. If I subtract the 1, I get y to the fifth plus y equals 0. And then I get this statement, y times y to the fourth plus 1 equals 0. Now the solutions that come from this part are going to be non-real. Okay, y to the fourth plus 1 equals 0. That's only true if you're working in the complex numbers, in the non-real complex numbers. So the only real solution here is y equals 0. So this implies that y equals 0. Okay, so let me fix this, right? So dy dx evaluated at x equals 1 is equal to dy dx evaluated at y equals 0, actually. Okay, so that's 1 over 5 times 0 to the 4th power plus 1. That would be just 1 over 1, which equals 1. All of that work for such a for such a simple answer. Oh well. Okay, but that's that. Okay, so that's why those two facts that we talked about kind of at the beginning of the lecture are important to us. But what I want to do now is take you through the derivative of exponential functions. Okay, so here we go, right? For b greater than 0, and the derivative of b to the x is going to be b to the x times the natural log of b. Now, why do we require that b be greater than 0? Well, because if b equals 0, then, well, this is just identically 0, right? 0 to the x power is just going to be 0, except when x equals 0 itself, and then you have some weird things happening, right? But anyway, so we don't want b to equal 0 because that's just not interesting. If b is less than 0, then b to the x is a really strange function. You should go to Desmos and type in like -2 to the x power. Put parentheses around the -2, but you'll see that strange things happen with that function. But anyway, so we let b be greater. Well, so in particular, maybe to clarify that a little bit more, like -2 to the x, what is that value when x is 1/2, right? You'd have to have the square root of -2, which is not real, right? So you get, if you let b be a negative number, then you get all of these really weird like non-real results. And so if we want to deal with real numbers only, we have to let b be strictly greater than 0. Okay, anyway, but this is interesting, right? Because the derivative of this function is just this function again times the natural log of the base. So in particular, if the base happens to be e, well, then the derivative of e to the x is just itself. So e to the x is funny that way. It's its own derivative. It's the only function that I know of that is its own derivative, right? Which is really kind of cool. So derivative of e to the x is just e to the x, okay? Because, I mean, according to this formula, it would be e to the x times natural log of e, but natural log of e is just 1, right? So anyway, but let's prove that this is true, right? So we're gonna do this proof the same way that we did the proof from earlier, right? We're gonna say let y be b to the x. What does this mean? Well, if we rewrite it in logarithmic form, this means that x equals log base b of y. Okay? And now we can differentiate both sides of that equation. Derivative of x is just 1. Derivative of log base b of y, well, we talked about this one. Right? This is 1 over y times natural log of b times dy dx, right? You've got to do the chain rule because we're doing implicit differentiation. But now if we want to solve for dy dx, we would divide through by this value, or rather multiply through by y times ln of b, and we get this. And what was y? Well, y was b to the x, right? And that concludes that proof. So let me give you a few examples of this fact in action. So let's calculate y prime if y equals 2 to the x. Right? So y prime is going to be itself, right, 2 to the x times the natural log of the base. Okay? And that's really all there is to it. Let's do another one. Let's do y equals e to the -2x. This one's going to require chain rule, right? Because we've got the e to the x function, but it's being composed with a -2x function. So, but the outer function is, e to the x. So we would say y prime is the function itself times the derivative of the exponent, which in this case is -2. So that's -2e to the -2x. Okay, that's due to the chain rule, right? to maybe drive that point home a little bit. Like, let's say that we had y equals 3 to the negative 4x or something like that, right? Y prime in this case would be the function itself, 3 to the negative 4x, times the natural log of the base, okay, and then times the derivative of the exponent, because you have to use chain rule on this one, so it would be times negative 4. So that derivative would be negative 4 ln 3 times 3 to the negative 4x, right? Something like that. Well, it would be exactly that, but there are lots of ways to write it. Anyway, so hopefully you see the difference between these three examples, right? Like here we're multiplying by ln of 2 just because the base was 2. Here we don't need to multiply by ln of e because, well, ln of e is just 1, okay? But we are multiplying by negative 2 though. That's because of the chain rule, okay? That's because of the chain rule. And here you have both scenarios, right? The base is not e, so you have to multiply by ln 3. And then you also have to do chain rule because of the negative 4x and the exponent, okay? Okay. Well, let me give you another one. Y equals e to the x cubed. So exponents within exponents. Y equals e to the x cubed. So y prime would be, well, the function itself times the derivative of the exponent, right? X cubed, derivative of x cubed is 3x squared. Right, so this is 3x squared e to the x cubed. Okay, one more. Pause the video, see if you can do this on your own. Y equals e to the cosine x. Give it a try. Okay, so this is going to be y prime equals the function itself times the derivative of the exponent. Derivative of cosine is negative sine. So that's negative sine sine x times e to the cosine x. I don't know if there's a nice way to write this, I guess. We'll say something like that. Okay, so I think you have the idea. Well, I hope you have the idea with exponential functions and their derivatives. Let me show you another use of this idea. Do I have room to squeeze this in? I think I can probably squeeze it in on this page. So let me give you another use of this idea. So let's use logarithmic differentiation to find the derivative of x squared plus 1 to the sine x. Okay, here we go. So we're going to use logarithmic differentiation. What does that mean? Well, it just means we're going to take the logarithm of both sides before we get started. So in other words, I'm going to say, let's let y equal x squared plus 1 to the sine x, right? The thing that we're trying to differentiate. Then I can take the natural log of both sides. And I get natural log of y. Taking the logarithm allows me to pull the exponent down. So I can say this equals sine x times natural log of x squared plus 1. Okay. And by the way, before I get carried away and get ahead of myself, this is a good technique for this particular problem because we don't know how to take care of issues like this where you have a variable in the base and in the exponent. If you just had a variable in the base but the exponent were a constant value, well, we could just use the power rule for that. Okay, and that's not a big deal at all. If you had a variable in the exponent but the base was a constant, well, we just figured out how to deal with those things, right? So that also wouldn't be a problem. But when you have exponents in the base when you have variables in the base and in the exponent, that's a situation we don't know how to deal with. And so what taking the logarithm of both sides allows us to do is it allows us to get that exponent down. So that sort of eliminates that issue. Okay. Okay. And now we can differentiate. We can use some implicit differentiation, right? So we can say, what's the derivative of ln of y? That's going to be 1 over y times dy dx. And then we would use a product rule here, right? So we say derivative of the first times the second plus the first times the derivative of the second. Derivative of ln of x squared plus 1 is going to be 1 over x squared plus 1 times 2x, right? Chain rule. So it's 1 over x squared plus 1 times 2x. Okay, we can clean that up a little. 1 over y times dy dx equals cosine x times ln of x squared plus 1 plus 2x sine x over x squared plus 1. Okay. Okay, and then we can multiply through by y to solve for dy dx, right? Times y. Okay. The final step, of course, would be to say, well, what was y? Well, y was x squared plus 1 to the sine x power. So I can take this one step further, call this cosine x ln x squared plus 1 plus 2x sine x over x squared plus 1 times y, which is x squared plus 1 to the sine x. And there's your derivative, right? Isn't that nasty? Starting with this kind of almost deceptively simple looking function, you get this kind of nasty answer. But there you go. That's how you would handle that, right? So the importance of understanding this particular example is to note that what we're dealing with in this chapter are functions of the form, base to an exponent, where this is just a constant number. In the past, we've seen things like a variable raised to some constant power. So we know how to take care of both of these situations, but what this example illustrates is how to take care of situations like that, where you have a variable being raised to a variable, right? What do? Well, you use logarithmic differentiation for that. Okay. So that's it for the exponential functions. I want to look at the inverse trig functions now. So let's take a look at the inverse trig functions, the derivative of those. And I'm only going to prove one of them. I'm only going to prove one of these formulas. The rest of the formulas are proved in a similar fashion. Okay. So actually, let me just show you the formulas first. Right here they are in all of their glory. Okay. So derivative of sine inverse is 1 over square root of 1 minus x squared. And you may think, well, that's kind of fantastic because this derivative doesn't even have any trig in it, which is kind of nice. And you'll see why that happens in a second when I show you the proof. But look what is also really nice about this is that derivative of cosine inverse is just negative 1 over square root of 1 minus x squared. That's just negative, the negative version of this one, right? So sine and cosine go hand in hand in that way. One of them's positive, the other's negative. Right? Same thing goes for tangent and cotangent, right? So derivative of tangent inverse is 1 over 1 plus x squared. Derivative of cotangent is negative 1 over 1 plus x squared. Okay? And then same thing goes for secant and cosecant. Derivative of secant inverse is 1 over absolute value of x times the square root of x squared minus 1. Derivative of cosecant is just the negative version of that same thing, right? So it's really kind of interesting. But anyway, I'll show you the proof of this one, right, of the sine inverse function. So we're going to prove it in a similar fashion as we've proved the other things in this section. That is, we're going to say, let sine inverse of x equal y. What does that mean? Well, that means that sine of y equals x. We can differentiate both sides of that expression. Right? Derivative of sine y would be cosine y times dy dx. Right? Implicit differentiation there. And then that equals the derivative of x, which is just 1. So then solving for dy dx, we would divide through by cosine y. We get dy dx equals 1 over cosine y, which I suppose you could call secant y if you like. But I'm not going to do that. I'm going to say, what I will say though is that, well, what was y? Y was sine inverse of x. So 1 over cosine y is really 1 over cosine of sine inverse of x. And you might think, well, but that doesn't look like the formula that we were supposed to get, right? That doesn't look like 1 over square root of 1 minus x squared. Well, it does if you do a little bit of trig on it, right? So remember, sine inverse of x is y. So if we draw a little right triangle and we label this angle y, right? Remember, sine of y equals x, and sine is opposite over hypotenuse. So this is x over 1. So it's opposite over hypotenuse, x over 1. The remaining side we can label a, and then use Pythagorean theorem, right? A squared plus x squared equals 1 squared. And then solve that for a, you get a equals square root of 1 minus x squared. Okay? So now we can look at, well, what's cosine of sine inverse of x, right? What's cosine of sine inverse of x? Well, it's cosine of sine inverse of x is just cosine of y, right? Because sine inverse of x equals y. And what's cosine of y? Well, cosine of y is a over 1. It's adjacent over hypotenuse, right? A over 1. And what's a? Well, a is square root of 1 minus x squared. So cosine of sine inverse of x is just the square root of 1 minus x squared. And thus, dy dx equals 1 over cosine of sine inverse of x, right? That's kind of where we left off with up here. But cosine of sine inverse of x is the square root of 1 minus x squared. So dy dx is 1 over square root of 1 minus x squared. And that concludes the proof. Like I said, the other proofs are similar to that. Okay? But let's take a look at a couple examples. I'll show you these formulas in action. Okay, so let's find dy dx if y equals sine inverse of x cubed. Okay, so dy dx, first of all, it's going to be the derivative. This is a composition of the sine inverse function and the x cubed function, right? But the outer function is sine inverse. And what's the derivative of sine inverse? Well, we just saw that the derivative of sine inverse is 1 over the square root of 1 minus x squared. Now it's important that for x you put in this entire argument, right? So it's not just x squared, it's really the argument squared. So it's really x cubed squared. Okay? But then remember chain rule. Okay? So this is the derivative of the outer function. And then we need to multiply that by the derivative of the inner function. Right? Derivative of x cubed is 3x squared. So cleaning that up a little bit, we're going to get 3x squared over the square root of 1 minus x to the 6th. And that's pretty clean. So so that's our final answer. Okay, let me give you another example. Let's do y equals secant inverse of e to the x. So I'll let you give the video a pause. Go ahead and try that one out and see if you can find that derivative. Okay, here's my solution. dy dx. Well, it's going to be the derivative of the secant function, which is 1 over absolute value of x, but by x we really mean, you know, the argument, right? Times the square root of the argument squared minus 1. Right? That's the derivative of the secant function. That's the derivative of the outer function. But then chain rule, right? We've got to multiply by the derivative of the inner function, which would be derivative of e to the x, which happens to just be itself, right? So what do we get? We get e to the x over absolute value of e to the x times the square root of e to the 2x minus 1. And there's some algebra that you could do there to possibly simplify that. E to the x is always going to be a positive number, right? Because if you plug in like a positive number for x, then e to the x is obviously going to be positive. But even if you plug in a negative number, like if you plug in negative 10, right? E to the negative 10 is just 1 over e to the positive 10. That's a really small number, but it's still a positive number, right? So these absolute values really aren't doing anything. We can drop them and just call this e to the x over, well, e to the x times the square root of e to the 2x minus 1. And then those things cancel. So dy dx in this case is just 1 over square root of e to the 2x minus 1, which is actually really pretty nice. Okay. And that's that, right? That's that one. So, and those are all the examples that I have for you from this section. So that's all for now. Talk to you later.